All right, day 2, we're going to be dealing with geometric series. We've already seen this formula both in Algebra 2 pre-calc and earlier in this class. And the infinite sum is simply term 1 over 1 minus r, which stands for the common ratio. Let's try a few. Find that sum. Again, a lot of people think, oh man, it's going to be infinity every time, but it won't be. It won't be here. Term 1 is 32 over 1 minus r, but r, that's what you're multiplying by, is 1/2. If you ever have trouble finding r, just pick a number, any number. How about this 4? And divide by the number in front of it. There you go. R is 4/8, which reduces to 1/2. And this works for any two numbers. You can try 8/16, that's a half, 2/4, and so on. So anyway, 32 over 1 minus 1/2, that's 32 over 1/2. And of course, dividing by 1/2 is the same as multiplying by 2. So this is going to add up to 64. You can see that 64 is a reasonable answer because right away you've got 48. You're adding another 12 right here. You're already up to 60. That's 62. Adding the 1 will be 63. But you really start to fizzle out the whole rest of the time that you add, all the way out to the end of your life. The numbers you're adding aren't very large. And so you'll never get past 64. If you could make it to infinity, the answer would be 64. All right, same sort of deal. Term 1 over 1 minus r. In this case, r would be, let's try this, 3/4. You're multiplying by 3/4 each time. That's going to make 40 divided by 1/4. And of course, 40 divided by 1/4 is the same as 40 times 4. So that will be 160. 160. If you try the formula one more time, you get 20 over 1 minus r. See, this time r would be 3/2. 1 minus 3/2 would be negative 1/2. 20 divided by negative 1/2 is the same thing as 20 times negative 2, and that's going to be negative 40. So this all adds up to negative 40. No way. It can't possibly be right. What the heck? I thought this was a decent formula. How come it suddenly is not working? Because those are all positive numbers and they're getting larger. There's no way in the world they add up to negative 40. And the reason is you can only add an infinite series and find its sum if the infinite series converges. And 6 and 7 do converge. Number 8 diverges. The numbers are getting larger and larger and larger. They're going out of control. The answer to number 8 actually is infinity. It does add up to something that you can't reach. All right, so the formula doesn't work here. So just realize, let me backtrack a slide. This formula only works if the series converges. What does that mean exactly? The series will converge if r is less than 1. And more accurately, I should say the absolute value of r is less than 1. R needs to be between 1 and negative 1. If it's not, then the series will diverge like number 8 did. And if r equals 1, that's going to diverge as well. So I'll put an equal to there in addition to that. If you think of a series, let's say I start with a 5. And r is 1, so you keep multiplying by 1 each time. You can see that you can't add that. 5, 10, 15, 20, 25. What's that going to add up to? Well, it's going to add up to infinity. So the diverging, like I said, has the equal to as well. All right, this formula that I taught you only works with converging series. And many of the other things that we're going to learn about only work if the series converges. And so we're going to spend a lot of time this chapter determining if things converge or diverge. Here it's kind of obvious, but it's not always obvious. Determine whether each series converges or diverges. This might be the easiest thing I'll teach in the whole chapter. What you do is you look at the summand, and this ends up being the R right here. R is 5/6. I put that 4 there to see if people would try to make it into 26ths, but the 4 is not being affected by the exponent of the n minus 1. The 4 can just get kicked out. Whatever this summation adds up to, if the 4 is outside, you're just going to quadruple it later. That's the same thing as quadrupling it term by term. So the 4 has nothing to do with the R. The R is 5/6. 5/6 is less than 1. So number 11 will also converge. All right, this is really cool. Write each repeating decimal as a fraction. Do that first. Then as a geometric series. Okay, let's start out by writing it as a fraction first. 0.58585858, and it repeats on forever. Anything that repeats or terminates means just ends, can be turned into a fraction. And since this repeats, we can do it. Here's how I do it. I'm going to start out by just naming it something. I'm going to call this thing n. N will be 0.58585858 repeating. Well, if that's n, what would 100n look like? What would that be? And the answer is you move the decimal point over 2 places and you get 58.585858 repeating. All right, if I take 100n and I subtract n, let me just move this to the bottom here. What if I did some subtraction? Well, 100n minus 1n would be 99n. When you subtract on the right side, even though this goes on forever, so does this. They're going to cancel themselves out. And you're just going to be left with 58. Divide both sides by 99. And n, which is a letter I made up, is 58/99. And 58/99 is exactly 0.58 repeating. You can check it out on your graphing calculator. Just type in 58/99, hit enter, and you'll see 0.585858. Now realize that on the calculator, the last digit's going to round up. And since both 5 and 8 are 5 or higher, it's going to round up to either a 6 or a 9 at the end of your screen. But that doesn't really happen. It does go on forever. All right, so that's writing it as a fraction. Now I'm going to write it as a geometric series. Okay, again, if n is 0.58585858, you can break it up like this. N is 0.58 plus 0.0058 plus quadruple zero, 4 zeros, 58 plus, and this will go on forever. That way when you add them up, the 0.58 occupies every 2 spaces, there's no overlap. But really, what I've made is a series. I've made a series, and the series is geometric. If you notice, what am I multiplying by each time? And the answer is, I'm multiplying by 0.01 or 1/100th. So here it is. We start with 0, which is pretty customary. We go to infinity because this never ends. I put the 0.58 right here in the summand. Right next to it is the R to the N. Okay, that's the answer, but let's verify that that's correct. If I put a 0 in, what would happen? Well, 0.01 to the 0 is just 1, so I get the 0.58, and yeah, that's what I want. If n is 1, then it becomes 0.01 to the first times the 0.58. That's going to give me this, 0.0058, and so on and so on. As n gets larger, you're going to keep multiplying by 0.01 each time, and you're going to keep getting all the next terms of this infinite geometric series. So yeah, there you go. So the two answers, as a fraction, it's 58/99, and then as a geometric series, it's the blue answer that I have in that box right there. All right, let's kick this up a notch. Maybe you have something where part of the decimal repeats, but part doesn't. It's 0.423232323. This will be a little bit more challenging. I'll start by calling this decimal n, as I did before. All right, I wrote the 2-3 twice just to emphasize that it's repeating, the 4 is not repeating. All right, if that's n, then what would 10n be? And the answer is, well, it would be 4.232323. The reason I multiplied by 10 is I wanted the 4 to be on the other side of the decimal point. Now, again, since this pattern repeats by 2's, I'm going to throw 2 more zeros into the mix. So instead of 10n, I'll say 1000n. And that's going to end up being 423.2323 repeating. All right, once again, we can subtract. (1000n minus 10n will be 990n. And even though these decimals both roll on forever, when you subtract, they cancel each other. And you just get 423 minus 4, which will be 419. Divide both sides by 990. And you'll have your answer of 419 9/90ths. And if you try this on your calculator, if you type in 419 over 990, hit enter, you'll see that sure enough, you get the exact decimal that you want, the 0.4, which will not repeat, 23232323, which will repeat forever. Wow. All right, so that's the first part. I wrote the repeating decimal as a fraction. And now I want to go ahead and do the geometric series part. All right, let's start right here with this n equals 0.423323. Let's bring it over to here. N is 0.4 plus 0.023. I had to leave a space because that 0.4 would occupy where the 0 is. Plus 0.00023. And you get the idea, it just continues on forever. Each time you're multiplying, again, by 1/100th or 0.01 to move it over a couple places. So the sigma is going to be this. The 0.4 needs to be out front. And then the rest of it will turn geometric. A little trickery there. The initial term will be the 0.023. And r, here in parentheses, is 1/100th to the n. So again, when you put the 0 in, you're just going to get 0.023 times 1, which is what you want it to start with. And then this will cause it to multiply by 0.01 every time, making a couple extra zeros in the decimal. The 0.4 out front just simply gets added at the end, giving you what you need. So there is the geometric series. We'll start with a bouncing ball. It's like one of those super balls that you kind of can get out of a gumball machine, 25 cents, and it bounces forever. Usually as a little kid, you lose it and it bounces across the parking lot. You get yelled at. Let's say you would drop this ball from a height of 10 feet, which is like a basketball rim height. And it begins bouncing, but obviously with friction and everything, it's not going to bounce all the way back up to 10 feet. It's going to bounce 4/5 or 80% as high every time. Find the total vertical distance traveled by the ball. It doesn't matter if you fling the ball out in front of you, if the ball has a little bit of an angle to it. It's still going to travel up and down vertically the same amount of distance, regardless if you drop it straight down or not, or if you push it out. All right, so anyway, this ties in directly with what we're learning in this chapter because we have to express this as a sum. All right, so when the ball's dropped, it's going to travel 10 feet vertically. Again, ignore the slant on that. I wanted to be able to have you guys see each bounce rather than having them all superimposed. But that 10 feet is the vertical distance straight down of that. So that's obviously part of the answer. But everything else is going to be doubled. Because what goes up must come down. Those two red pieces are going to be congruent. These two green ones, same thing, are going to be congruent. Same for the blue, and so forth and so on. And together, this part of it is geometric, and it's converging because R is 4/5, or 0.8. Let me just do some quick computations here. 10 feet times the 4/5 will be 40/5. That's going to be 8. So the ball's dropped from 10 feet. It bounces up 8 feet in the air from there, which sort of makes sense. That's 80%. But then the 8 feet, it has to fall 8 feet as well. Oh, man. The next one, the green, if you take that 8 and you multiply it by 4/5 or 0.8, the green is going to be 6.4 feet each time. The blue will be 5.12 feet. In both directions. And theoretically, this ball would bounce forever if you used my model. Truth be told, friction's going to eventually stop and it's going to come still on the ground. But the numbers that we would be adding if we added all the way to infinity would be so small that you wouldn't even be able to detect them. Even if you were tiny like an ant along the ground, you wouldn't be able to see the ball moving. It's just such a small number. So anyway, let's figure out what this all adds up to. I have the 2 out front. So basically we're adding an 8 plus a 6.4 plus a 5.2 and so on and so forth. What does that add up to? Well, it is geometric and it is converging. So we can use the red 8, that's term 1, over 1 minus R, and R is 0.8. That's what I'm multiplying by each time. That's that 4/5. That's going to be 8 divided by 0.2. If I think of the 8 in the numerator as 8.0, which it is, I can slide both of these to the right one space. That's 80 halves, that's 40. So the parentheses is just a big 40. And the parentheses is much larger than it needs to be. I guess I was anticipating something crazy. Instead, I have 80 plus 10. This ball is traveling a grand total of 90 feet vertically. All right, cool. Find the common ratio of the geometric series. Once we have that, write the function that gives the sum, okay? Graph the function and the partial sums S3, S5. What do you notice? Okay, well, let's take a look. First off, the common ratio, what are you multiplying by each time? Going from 1 to 2x to 4x squared to 8x to the third. Obviously, you're multiplying by 2. and by x, but since the signs are changing, you're also multiplying by a negative. So the common ratio here is negative 2x. And of course, the formula for sum, as we well know, is term 1 over 1 minus r. Term 1 is, of course, the 1. And 1 minus negative 2x will be the denominator. We can definitely clean that up a little bit. That's just going to be 1 over 1 plus 2x. Okay, so that's that. Okay, so far we've got the common ratio. We've got a formula that gives the sum. And then we want to graph the function in the partial sums, S3 and S5. What is S3, first of all? Well, it's the sum of the first 3 terms. It's just going to be this. This is S3 right here. And S4 would include this. S5 would include the next one, which I think it's pretty easy to see would be 16x to the 4th. That'll be positive. So that's S5. All right, the last thing I need to do is graph the original function, which is there in blue with the light yellow background, 1 over 1 plus 2x. And then I'm going to graph the S3 and S5, and we'll just see what we notice. I'm going to use green globs for this. Okay, here is the original equation. This is the perfect answer. This is what we got using the infinite sum formula. It's 1 over 1 plus 2x. And there's its graph. All right, now they want us to also graph S sub 3 and S sub 5, which is the third partial sum and the fifth partial sum. So I'll start that just by going y equals, and yes, that is an equal sign. I know you can't really see the top prong. It's like really light gray for some weird reason. That happens a lot on my smartboard. So y equals, we started with 1, and we were multiplying by negative 2x each time, if you remember. So 1 minus 2x plus 4x squared. All right, that's S3, the third partial sum. Let's see what that looks like. Okay, very interesting. Right around the point 0, 1, it's perfect, and then it kind of pulls away from the red graph. Remember, the red graph is the perfect answer. That 1 over 1 plus 2x would be if we added all the way up to infinity and actually made it to infinity. And the green is just us being lazy and only adding the first 3 terms together. So I would expect it to be good right around 0 and then start to pull away and be less accurate. Let's tack on the next 2 terms and do the fifth partial sum, S sub 5. Okay, let's see what that gives us. It's a little tough to tell. That is an improvement. Let me go ahead and zoom in and you'll see a lot more clearly what's going on here. All right, as you can see, when I zoomed in, the perfect graph was the red. That was the infinite sum. The green, which was S sub 3, right at the point 0, 1, all 3 of these are perfect. You can't tell the difference between red, green, and blue. As you move away from the point, I should say 0, 2, I'm sorry, I said 0, 1. As you move away from the point 0, 2, you can see that green kind of pulls away first. Blue sticks with red a little longer, and then it pulls away. If I took this out as far as I can only get out to the edge of that box, you'll see that the graph becomes more and more and more accurate the more terms that I add. All right, this is all I can fit before I'm going to run out of room. Let's see what that does. S7. As you can see, it stays with it a little bit longer. If I got out to like x to the, 15th, 17th, 19th, I would be able to be on that red the whole way, and you wouldn't even know that red and pink were any different. So that's kind of where they're going, and this is actually a precursor to later on in Chapter 9. We get into Chapter 9, 7, 9, 8, 9, 9. We're going to be doing things like this. So this was just a little appetizer. I will say this, whenever you have a converging sequence or series, whether it's geometric or otherwise, you have a point called the center. And right here, the center of this thing is the point 0, 2, right here. You won't need to know this for section 9.2. This is sort of later. At the center, everything's perfect. All of these estimates are absolutely perfect. You could zoom in on the point 0, 2 500 times and you wouldn't be able to tell the difference between red, green, blue, and pink. The two things I want you guys to take away from this that we are going to learn over and over and over and use in the future is this. The more terms we use, the better the approximation becomes, and the closer our graph approximates the actual red series. Okay, so the more terms, the better. The higher the degree that we make it, the better off we are. And I think you can see that blue is a little better than green. Pink is a little bit more accurate than blue. And the second thing to take away is this. The farther from the center, in this case x equals 0, the worse the approximation. If I wanted to know, hey, the red graph, where is it at positive half here? If I go up. Well, it wouldn't matter if I used red or if I plugged it into pink. It would be about the same answer. Green would be a little less accurate because green's already pulling away. Blue is pulling away a little bit more than the pink is. But man, if I got out to positive 2 or positive 3 and I said, hey, use, where am I right here? And you're using blue or green as an estimate, you're like way off the page. And pink's way down here. That's a terrible approximation. So the farther away you get from the center, the worse you are. So you, again, want to stay near the center, and you want to add as many terms as possible. Both of those things will increase your accuracy down the road later on in Chapter 9. Have a great day, everybody. Take care of yourselves.